Hello again, everybody. Welcome back. So this video is going to be on indoor comfort, on the basics of indoor comfort, and specifically on a type of indoor comfort model called the predicted mean vote model. Now, that's a specific type. There are a few types of indoor comfort models, but this is the one that is commonly used by HVAC engineers. And so it's probably what you would use if you want to make an argument for a certain type of change in an HVAC system or a thermostat set point, those types of changes. And so I'm gonna walk you guys through this today. So PMV it's been around for a while. There are tons of calculators on the internet. Like this is one example here where you'd put in things like a metabolic rate. The ambient air temperature, radiant temperature, and it would give you out a predicted mean vote. And so what essentially I'm going to show you today is, there are many web applications that do this, but I have built one for Grasshopper here using open source functions that a wonderful group called the Center for the Built Environment sort of made open to all. And this is actually a model that is endorsed by ASHRAE, which is the American Society for Heating, Refrigeration, and I can't remember it all. But the key thing is that this is used for most HVAC applications. So I wanted you to drag and drop this component that you'd see. See, it's got a very long description because I'm trying to give you guys as much information as possible. But we'll cover all of this in the course of this video. So if you guys remember from the last video, it's very similar to the Universal Thermal Climate Index calculator. And that you have these inputs, the same type of inputs, and you get out a value that is the standard effective temperature, which is what the temperature feels like. But the nuances of this model are that you can also put in a metabolic rate of the person, which varies from activity to activity. So you can be running, and that's obviously generating a lot more heat than if you're sitting still. And you can input clothing level. And this is, because of those inputs, this model is mostly used if you have specific values for those that you know exist in a condition that you're looking at. That's when you would use this type of model. So just to start off here, we're going to hook up some sliders, very similar to what we had done before, maybe 0 to 30 again for our dry bulb temperature, and we'll set it at 20. Radiant temperature, so we don't need to put in that, and you'll see it says it will assume that it's the same as the air temperature if we put in nothing there. Wind speed will also, it assumes a very low wind speed if we don't put in anything, so we'll just leave that blank for now. And we'll put in a relative humidity, and then just hook up a Boolean toggle and run it. And then you see we get out of this a standard effective temperature of what it feels like. And so you see it's a bit different than the UTCI. UTCI would probably have tend to stay closer to 20. But you can see, and it can change a bit with these parameters in the same way that UTCI changes. So the thing is, the interesting thing that made this predicted mean vote model really powerful and in its time when it first came out several decades ago, and that the air conditioning industry and HVAC engineers really like, is that it's been correlated to sort of a predicted mean vote. So essentially the way that this model was developed was that they took a bunch of real climate subjects, a bunch of people, and they put them in a very tightly monitored air-conditioned climate chamber. And these, the conditions were, really all these things were watched very closely: dry bulb temperature, radiant temperature, wind speed, and then they had ways of estimating metabolic and clothing level, which you could really only, do it well in a climate chamber. And they asked people, okay, rate on a scale from -3 being like you're really cold, you really don't like it, to +3 where you're really hot and you really don't like it, and 0 is your nice value. What is your vote? How is it too hot or too cold? And you can see this person right now is voting that it's too cold, and that's probably because our temperature is so low. But the thing is, if we raise that a little bit, you'll see, okay, it gets closer to 0, and then the person's a bit happier. So this is a mean vote, meaning that it's averaged over a very large group of people. So another way of understanding this, which was pretty useful, is in terms of the percentage of people that are dissatisfied, which is basically when the number of people where the predicted mean vote is less than minus 0.5 or greater than 0.5. And you see right now, this is like very comfortable conditions because only actually about 5% of people are dissatisfied. And I know actually, well, you may also be surprised as I was when I first started learning this, is that it's not possible to get 100% of people comfortable. You're always going to have some percent of people dissatisfied with this model. And that's predominantly because you're restricting people's metabolic and clothing rate. Which is, I mean, when you do that, you don't give the people the freedom to change their clothing. There's no way that you're able to make everyone happy. And that's also an important lesson to take away from this comfort model. But you can see, we can turn it up and like, okay, when it's 28 dry bulb temperature, you get 40% of people dissatisfied. So then you're in deep trouble. And most of the HVAC industry has just tried to keep it below 20. So 20% of dissatisfied. So this would probably work for most of the air conditioners and HVAC engineers' purposes. But the ambition ones will also try and get it, below 10%. So that's generally basically how this works. But so now the thing is, of course, I said the nuances are, well, actually, you know what, there's a little more to explain how this works. And for that, we're actually going to delve actually just very briefly into the code again, just to show you what's actually going on. So the thing is, I said that this was correlated to actual surveys that they did of people in climate chambers. But the thing is, the way it's actually calculated, this predicted mean vote, is that it does an energy balance of a human being. It actually runs the whole energy balance, which, if you remember in the last video, we were just using an approximation of things that had been run through a very complex energy balance model. But this one is actually doing that. And what it does, so you'll see things, let's see, we have to get all the way down to our so there's a bunch of functions in here, but we have to get, all right, here we go, all the way down to our predicted mean vote comfort class. And this is actually, so this is calculating it for elevated airspeed, but let's go all the way down to the basics, our function that calculates predicted mean vote. And you'll see here are those same values that you're plugging into the component here of dry bulb temperature, mean radiant temperature. Here, they're all here in this function. And you can see what it's doing is that it's essentially it's running through in sort of several iterations for each sort of minute of an hour. It's looking at the energy balance of the human, and it has things like heat loss by sweating. It has respiration. So it's all these like specific things. You'll see like blood flow, I remember, is one of the things here. But it returns a result, which is your predicted mean vote and percentage of people dissatisfied based off of this human energy balance calculation. So that's how it works. You get a general sense of what's going on there. But so now let's see. I mean, if it's doing all these things that are specific to the energy balance of the human being, then let's play around with these metabolic and clothing levels. So you can see, I mean, the nice thing about this is that you can say, well, all right, well, maybe we have a condition that's really cold, like it's 15 degrees. Celsius inside, which tends to be very cold, and your predicted mean vote is really low. It's most people would consider. I mean, 86% of the people say they're unhappy. But the thing is, you can say, well, you can start to make an argument. Well, like I actually know that people in this place are willing to wear enough clothing that might actually make these conditions comfortable. So you can say, let's make a slider that goes from usually people like socially acceptable levels of clothing are about 0.4. That's about shorts and a t-shirt, and the maximum that you might wear, one clo, which is what you input here, is a 3-piece suit. But maybe we can go up to 2, which would be like a kind of like 3 layers of clothing, something pretty thick. We're saying that we're in a climate where people actually are okay with this. So we can first start off with 1 klo, and it doesn't change too much. But we can say, all right, people are really going to actually wear pretty thick jackets in this place because I know it's a common thing. And you can see if we really boost that clothing all the way up to 2. We get down to about only 10% of the people are dissatisfied. And so you can understand, instantly, because especially if you're a designer and you know what your client is and you know what the occupants of your building are going to be doing, you can use this to start to argue for certain set points. So you can drop the temperature of the thermostat down to 15 and save a bunch of energy because you know that the clothing level is out there. So that's a brief thing of clothing. But now there's also things like activities. Which then correlate to the metabolic rate. So you'd see by default, this component is assuming that the person is sitting, and you see that didn't change there. But there are other ways that you can sort of make yourself comfortable in say like colder conditions. So say for example, so I actually, even though it can be very cold outside, I enjoy going for runs when it's something like about 5 degrees Celsius. So it's it's pretty cold for most people, even if you have this like thick jacket. But let's say I even go running in let's see, I'm running kind of shorts and a t-shirt still in this weather. So you see, I should be really like the predicted mean vote is way off the scale. Everyone's dissatisfied. This really shouldn't be any condition where anyone's satisfied. And if you were sitting, this would be the case. But let's say if I'm standing, okay, it's a little bit better. Let's see, if I'm strolling, if I'm walking, okay, actually then maybe it starts to get a little bit, maybe slightly within the range of tolerance. But let's say now I'm walking pretty fast, like getting close to jogging, like at 4 miles per hour. And suddenly, wow, look at that. It's only 5% of people would find this condition discomfortable. If you're walking, at a power walk, almost jog pace, your predicted mean vote's going to be close to 0, and so this is showing you that I can actually be pretty happy jogging in this type of weather. If it's 5 degrees Celsius outside, which is usually pretty cold. So okay, so you get a sense of this. But now, of course, like I'm sure you guys have been sort of watching what's over in this rhino scene here and wondering what it is for the past few minutes. The reason is because the really awesome application of this is that we can then use this for indoor comfort studies. And so you'll see that that I have an energy model set up here, and I'm not, it's a little bit complex, so I wasn't going to go through the whole thing in this video. And we'll post other videos on how to set up an energy simulation. And I'm just going to go over the basics with you guys. But the thing is, we can take results from this energy simulation, like our air temperature, radiant temperature, and relative humidity, and simply plug them into this wonderful component here, and get predicted mean vote values for every hour of the year. And for each of these, so you'll notice that these are kind of split here into different zones. And so the things we have 5 different parts of our building. This, I know it's a very simple box building right now, and you could run much more complex things through Honeybee, but I'm doing this just for the purposes of time right now, keeping it kind of simple. But you can see we have 5 different areas that each get different amounts of sun and are going to be at different temperatures at different times of the year. So if we want to use this with an energy simulation, I said I wasn't going to run through the whole thing, but the important thing to know is that you just have to request using this simulation outputs. Not glazing solar. We don't need that one. What you need to request are zone comfort metrics. So if you set that to true, this component is going to output the things that you need in order to run comfort analyses on your energy simulations. So you see it's doing operative temperature, air temperature, and these values, these simulation outputs, get plugged into the run energy simulation. And then there's one other thing I'll show you which is kind of important for this, which is a component that allows you to take your zones, which is your geometry here, and which we're visualizing down here, and that's what you guys have been looking at in the Rhino interface here. And it allows you to change the set points of them. So you can change the cooling set point. So right now it's set to start cooling at a very low temperature of 22 degrees Celsius. And the reality is, depending on the application, we could probably boost that up to 23, or maybe, actually let's put it up to 24. And so you guys can actually play around with these things. And maybe the heating set point really should be up a little bit higher, maybe around, say, like 20. We'll do 19. And so you can play around with these, and you see the changes in energy at the same time that you see the changes in comfort. And you can make arguments that spaces are still comfortable, even though the set points are lower or higher. And this, by the way, is a huge energy. For every degree Celsius that the temperature drops, that's 10% of the thermal energy. It actually ends up really saving a lot of energy. It's a really, potentially a big way to push sustainable stuff forward in the future. All right, so we've got that, and then, we've had this all set up, and so I'm just going to run this simulation, which is going to take just a few seconds, maybe like half a minute, where it's just going to run through essentially every hour of the year, to produce, to give us values of air temperature, radiant temperature, and relative humidity. And I think I'm just going to fast forward through this part so we can cut to the chase and do some comfort analysis. Okay, everyone, the simulation is finished, and you can see that our result importer here brought in the things that we requested, which were operative temperature, air temperature, and our comfort metrics, essentially. And just to show you guys exactly what comes out of this, I mean, it's essentially you have a grafted list of values for every single hour of the year in terms of operative temperature, air temperature, and so these are multiple lists. You get one for each zone, and to kind of prove that to you that you are getting that, we could use this Grasshopper param viewer, and you see there's 5 lists there for each of our 5 zones that each have 8,760 values for each hour of the year. So we can now take this and we'll do this now for all of our zones. Essentially at once, which is going to take maybe like a minute to calculate. And I know one zone itself probably takes about 10 seconds. But let's see, we're gonna set that to false while we set this up, and we'll just delete out these sliders. Let's set our activity back to sitting, because probably that's what most people are going to be doing in our building. And we'll delete the clothing and set it to the default of 1, a 3-piece suit for now. And essentially now what we can do is we can take the air temperature and plug that up into the dry bulb temperature. The radiant temperature, now we didn't have that before because we were assuming that the radiant temperature was the same as the air temperature, which might be okay if you're out in the middle of a field somewhere or a large room or something. But now that we have that, because we ran this big sophisticated energy simulation, we can plug that into there. And then wind speed, probably inside it's going to be close to 0 for most parts of the year, but you know that you can play around with that now after you run the simulation. And then we'll take the relative humidity and plug that into there. And then now it's going to take a few seconds to calculate, but I'm just going to set that to true. And it's now for each zone and for every single hour of the year, this component is going to calculate predicted mean vote and percentage of people dissatisfied for us, and standard effective temperature. And so we'll work with this once it's finished. But for now, I'm again going to fast forward through this just because it takes about a minute or so. And see you on the other side. Okay, everyone, our predicted mean vote simulation has finished, and you'll see what we're getting out of here now is that we get predicted mean vote values for every single hour of the year, essentially, for each of those 5 zones. And again, it's coming in as a grafted list. So I'll just pull up a param viewer again to show you one for each zone, essentially. And so now we can do stuff like I'm going to delete this again because we're probably mostly interested in predicted mean vote here. But we can plot this now on, say, like our 3D chart that you may remember from our last video. And I'm just going to set up the situation that I like here, where we essentially will scale the x by 0.25 and the z I like to set to 0. I'm just doing all this beforehand just so that, because it can take a long time to plot all 5 different zones. And so I'm just going to set it up beforehand. And then we'll also put in some legend parameters. We'll set a low boundary of the lowest possible. Well, let's see. I don't imagine us getting a predicted mean vote worse than 2 in some cases. And then we'll set the upper bound to be positive 2. And then plug those into our legend par. And then looks like we're basically ready. And then I'll do the preview I like with the graph curves and the swatch. And pardon the that I am sound there. Okay, all right, so now we're all set up and we're basically ready. We just take our predicted mean vote and we plug it into our 3D chart. And this is going to plot then predicted mean vote for each of these 5 zones for every single hour of the year. And we'll begin to get a sense of the fact that, well, certain parts of the building are comfortable in certain hours, certain others are not. And then you can imagine using this to make arguments that, maybe someone might move around the building to make themselves comfortable, and things like that. So this is going to take another few seconds. So again, I'm just going to fast forward it. Bear with me. Okay, all right, I finished making those 3D charts. It actually didn't take too long. It's only a few seconds. But you can see now what we get are these predicted mean vote values, which are displayed really nicely, and for each of our different separate zones. And you can see that there are generally some things that hold true, like it's, the predicted mean vote is warmer in the summer than in the winter. But you can also see certain opportunities that start, or problems that might start to arise. So in the red color here means that these zones are getting too hot in the summer, which are, specifically our south zones, and it looks like our west zone. So this must be our south zone, and this is our west zone, which is getting that direct sun in the afternoon after 6 p.m. So you can really, start to piece through this and understand the potentials of what's going on. And you see, okay, but the north side is really comfortable at that time, so that should work. And then the blue means that it's getting too cold, but the south zone is a great place to be in that time in the winter. So you get a sense of the potentials of this. And that's sort of going to wrap up. I mean, there's one other thing I'll mention here that, because people's clothing are actually going to change on an hourly by hourly basis, I have a small component here that allows you to essentially calculate the people's clothing values for every hour of the year, and you can then plug this into this component here to change that. But I'm not. The video's already run so long that I'm gonna cut it short for now. And you can, if you want to know more about this, you should get everything you need in the description. All right, everyone. Well, I'll see you in the next video where we're going to look at adaptive indoor comfort, which seems to be a sort of area of a lot of future potential. And so I'll see you on the other side.